Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3 Finite Difference Solution of Linear Two-Point Boundary Value Problems. Example. Let us consider the following second-order two-point boundary value problem. We will use the finite difference method to obtain an approximate solution to the given problem using h equals 0.2, 0.1, and 0.05. Then, we will compare the estimates with the given true solution. In the gridding step, we create discrete nodal points for which the approximate solutions will be obtained. First, the solution interval is divided into 5 uniform subintervals, giving h equals 0.2, and nodes are placed at the endpoints of every subinterval. The nodes are enumerated, starting from 0, and the abscisses corresponding to the nodes are calculated from xi equals 0.2i, I equals 0 through 5. This illustration depicts the uniformly spaced grid structure. The y values, i.e., ordinates, corresponding to the abscisses are shown representatively. At the left boundary, y'0 is 0, which implies a symmetry boundary condition. Due to the Newman boundary condition, we place a fictitious node to the left of x0 equals 0. At the right Dirichlet boundary condition, y1 or y sub 5 is 4. The unknowns are the ordinates corresponding to nodal points from 0 to 4. The ordinary differential equation is discretized at a node xi, and the first and second derivatives are replaced by their central difference approximations. The given two-point boundary value problem is satisfied for every x from 0 to 1. The differential equation for the ith nodal point, x equals 11, is expressed as follows. Replacing the derivatives with the central difference formulas yields. Collecting similar terms, we obtain the general difference equation. The difference equations for the unknown nodal points obtained by applying the general difference equation yield. The difference equations for I equals 1 through 3 are final. For I equals 0 and I equals 4, there is a bit more work to be done as we still have to implement the boundary conditions. The left boundary is a Newman boundary condition. y'0 is equal to 0. This leads to a fictitious node and corresponding value, y sub minus 1. We discretize the left boundary condition and solve for y sub minus 1 as follows. Substituting this into the difference equation, we obtain the right boundary condition is Dirichlet boundary condition, so we can write y5 equals 4. Substituting this into the difference equation, we obtain in the fourth step, we have obtained 5 difference equations and 5 unknowns, y0 through y4. Using the difference equations, the unique 5 by 5 system of linear equations is put in the matrix equation form to be able to use a matrix solver. The system in matrix form can be expressed as follows. The resulting system of tridiagonal equations is solved using a tridiagonal solver. For m equals 5, we find. We repeat the numerical solution steps for m equals 10 and 20 without going into details. And for m equals 10, we obtain the true solution and approximate numerical solution, as well as the absolute true errors, are presented in the following table. The last row is the Dirichlet boundary condition. The numerical solution for m equals 5 was obtained with steps of 0.2, and the error is proportional to 10 to the minus 2. In the next column, the absolute true error for the m equals 10 case is tabulated, which depicts errors in the order of 10 to the minus 3. In the last column, the absolute true error for the m equals 20 case is presented. As the interval size is reduced, the true absolute errors are in the order of 10 to the minus 4. We observe that as h decreases, the numerical estimates approach the true value. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.